All right, so this is our last curve sketching. We're going to be using a trig function. And so we take our tangent with the 2x, and if you graph it, you get this really cool looking function. But we've got a lot of points of undefined. So what we do when we do these problems is we adjust the window. We look at just one. So negative pi over 2 to pi over 2. And then now when I graph it, we get this instead. So we can look at just one of them, but you can see that we are getting a minimum and a maximum, and we're getting a concave up, point of inflection, concave down. So we're getting some points that we can find using calculus. So domain, we don't have to worry about anything. It is from negative pi over 2 to pi over 2, because pi over 2 and negative pi over 2 is where tangent has issues. Vertical asymptotes, we're going to be getting them at these 2 points. So at x, oops, let's put those in red. At x equals negative pi over 2 and x equals pi over 2. This is just standard for tangent. And so because of tangent there, we still have that same situation. So at negative pi over 2, we've got a, let's move that over a little bit. We've got a vertical asymptote. And then over here at pi over 2, we also have a vertical asymptote. So when you're dealing with your tangent, cotangent, secant, cosecant, you want to include those vertical asymptotes. All right, so now we're going to take the first derivative and find all of its info, and then the second derivative and find all of its info. So let's just put the first there so we can just transfer it. All right, so first derivative of this would be 2, and then the derivative of tangent is secant squared x, and then again we set it equal to 0. So if we solve for secant x, I'm going to do that over here. It would be square root on both sides, so we end up with plus or minus square root of 2. So like that, plus or minus. All right, so we look at our unit circle, and secant is the reciprocal of cosine, so our radical 2's are here for them, and it's from negative pi over 2 to pi over 2 is what we're looking at. That was our domain given. So we're going to be getting x right here at pi over 4, and then also here at 7 pi over 4. So at pi over 4, our x would be rad 2 over 2. At 7 pi over 4 would be rad 2 over 2. So we don't have to worry about the negatives because they're outside of our domain. So pi over 4 and negative pi over 4. So x equals pi over 4 and negative pi over 4 because of our domain, which is from negative pi over 2 to pi over 2. And we don't care about these regions. So now if we place those points on there, one here at negative pi over 4, and one here at pi over 4, and resist the urge to put 0, because we don't want to do that. We're looking for intervals. And then we now test our derivative. So something in between there, you can again pull up the unit circle and easily find it. So between pi over 4, negative pi over 4 and negative pi over 2, we would get negative pi over 3. And pi over 3 on the outsides. So negative pi over 3 and f prime of pi over 3. And then you're going to hate me in a minute. And then something in between negative pi over 4 and pi over 4, how about 0? All right, so at negative pi over 3, that's this one, we get a half. And so what we're going to do is flip it, and that makes it 2. So we'd get 2 minus 2 squared. That's negative. So we know it's negative, it's decreasing. And then we move into 0. And cosine of 0 we already know is 1. So 2 minus 1 squared, again, would be positive. So we know that area is increasing. And then on the end part right here, f pi over 3 is just going to be the same situation here. We're going to end up with 2 minus 2 squared, which again is positive. Or sorry, negative. So it's negative and it's decreasing. So we're going to be getting a local min here at negative pi over 4. So let's test that. Trace negative second pi divided by 4, hit enter, and it says negative 0.570793. Let's find the exact So we have y equals and 2, and we're going to do pi over 4 first. And then we'll plug in negative pi over 4. And the reason we're plugging this, there's still a nice, we're going to do exact values. You can use the decimal if you want, but pi over 4 tangent's 1, and it's negative 1 for negative. So this would be just pi over 2 minus 1, and this would be negative pi over 2 plus 1. So now we know our exact values. So this would be pi over 4, comma, that, and this would be negative pi over 4, comma, that. All right, so let's place them where they need to be. So for the negative pi over 4, that was a min right there. So that is our local min, negative pi over 4, comma, negative pi over 2 plus 1. And the other one is a max, pi over 4, comma, pi over 2 minus 1. Okay, intervals of increase. So it is increasing from negative pi over 4 to pi over 4. And it is decreasing from negative pi over 2 to pi over 4. And then also, negative pi over 4. And then also from pi over 4 to pi over 2. So both the negatives and both the positives. All right, looks good. And so we have our concave down, concave up. So now let's place these 2 points on there because they are our critical points. Let's place them where they need to be. And it doesn't have to be perfect, just you can get exaggerated. So we know this one is at a negative, and you can verify that just by using the trace function. So trace, and then plugging in your negative pi over 4, and it's going to tell you it's in the negative. You can see that one's in the positive. You can also plug these in your calculator to verify where they are, but it's pi over 4 is dead center, so we already know that's pi over 4. Put a dot, pi over 4, and then pi over 2 minus 1. And then the other one is over here. And you may be asking, if you have the calculator, why are we doing all this? Well, it's going through the steps. The calculator there is to help you make sure that all your work is correct. You still have to do the work. You have to do these analytically. So might as well have a calculator there to make it checkable. Okay, so we're going to take that 2 minus secant squared x and rewrite it here. And that's 2 minus, and parenthesis, secant x squared. So we're going to have to use chain rule. So I'm going to do f prime on the side over here. F double prime now would be 0 minus, and then 2 secant x to the 1 times the derivative of the inside. So what is a derivative of secant x? That's secant x tangent x. So our f double prime of x is equal to negative 2 secant squared x tangent x, and then we set it equal to 0. So again, this would be secant squared x equals 0 and tangent x equals 0. Those are the 2 factors that we're multiplying. You don't have to worry about the 2 because it's 2. It's not going to make anything, but it will affect our positives and negatives for our second derivative. All right, so if we pull up our unit circle, we're looking to see when is our cosine, right? Because that's our reciprocal. So this is just 1 over cosine squared x equal to 0, right? And then you ask yourself, is that possible? No, it's not. So we say that this cannot equal 0 because that cannot equal 0, and we just move on to tangent. So when does tangent equal to 0, right? That's going to be our, this is y over x. When we look at it, it's our sine over cosine. I should really write that. Sine x over cosine x equals to 0. So we're really just looking at when does sine x equal 0. That's what we're applying. So when does our y coordinate equal to 0? So right there. So right at 0, because we're only going from negative pi over 2 to pi over 2. So it's right here at 0. So that means x equals 0. We go back to our graph. Again, you still want to make sure you put negative pi over 2 on there, cross it off. Put pi over 2, cross it off. And then we put our number right in the middle, 0, and we test. So f double prime of negative pi over 4 again, and f double prime of pi over 4. Now up here, that was a subtraction, so we actually had to do some subtracting. Here, it's multiplication. So secant squared is always positive. So really what it is negative, positive, and then we got to find it. So we already know it's negative, positive, and then tangent. Negative, positive, and then tangent. And it's fairly quick because tangent is negative in this quadrant, which would give us a positive. It's concave up. And then we go to our calculator and check. Concave up. Perfect. And then tangent is positive in the first quadrant, right? Remember? Tangent here, because these are all negatives over positives. That's negative. That's positive for tangent. So we put a positive there for it, which means it's negative, which means it's concave down. So do we have a point of inflection? Yeah, it's at 0. And you can use your calculator. It's very quick on this one, though, if you want. Trace 0 is 0. So we know that point is 0, 0. And then it's concave up from negative pi over 2 to 0. And from 0 to pi over 2, it's concave down. And so now we just need to put these points on there. So 0, 0 also needs to be on there. All right, I'm not going to mark it, though, because that is the origin. And then now we just do our concavity. So from negative pi over 2 to 0, it is concave up. And so you just have to trace that in there. Concave up, and then asymptote. And then from 0 to pi over 2, we have concave down. And so just make sure as you connect from point to point, you're using that concavity that we used before. That looks horrible. Let me try that again. I can zoom in. Concave down. So make sure each region from point to point has that situation. So as we go from this point to this point, it has that concave down. And from this point to the asymptote, it's concave down. And then these are concave up. So it has to have that concave up, concave up. See, that one looks kind of funky. So I'm going to erase that one and redo it. Concave up. Perfect. Concave up. Perfect. So it's exaggerated. And there you have it. There's a crazy trig function.